So right through steps, we can well imagine control unit detects a miss, control unit requests a memory to replace the cache line. Memory start transferring the block into the higher level memory, control unit is stalled. Okay, so very well. So this is the worst case scenario. Control unit trying to write into a address. The address itself, that block itself is missing at the L1. Okay. Now once the block transfer is done, control unit writes that data to the cache block, L1 cache block, and control unit requests the memory to write the same data into the lower level memory. Okay, so now you are copying from the higher level memory that block to the lower level memories. Maybe, well, you can optimize it like why the entire block, only that data gets into that into the lower level memories. That's a different thing. It's added complexity on the circuit, but it's doable. But even then, it slows down. Like it holds the control unit until memory management unit is done with the data transfer. So once done, MMU issues the down signal, and then control unit starts again after the memory write stage. Okay. So right through, the advantage is that it is simple strategy, simple circuit, no impact on the read operation whatsoever. Its disadvantage is control unit is stalled twice, high impact on the performance, as I explained. So here is a flow chart which explains the whole process. So memory requests come from the processor or control unit, right? And we check it's is it a read or a write. Well, if it is a read, then is it a cache line hit? Is the hit on the cache? Yes. Okay, return the data, done. If it is no, then find the cache line to replace, copy the block from the lower level memory, and then return the data. Then you are done. So these two parts, find a cache line to replace and replace that line from the lower level of block, that's where your processor is stalled because it's a slower operation. How about the write now? Okay, if it is not a read, it's a write, is a cache hit. Okay, yes, write the cache data, write the data into lower level memory. So that's one stall and you are done. Now, if it is not a cache hit, okay, then find the cache line to replace, copy the block from the lower level memory, then write the data into cache, and then you write down that same block to into the lower level memory to maintain the consistency of the information between the blocks across the hierarchy of the memory. So you see, in this worst case situation, we are going through two stall mode, right? One, when we are trying to find out the block and replace the cache line, so that's one stall, and then we write the data and we need to then write back that block immediately to the lower level of memory. So that's become another stall. Now second stall is coming from expensive write operation at the lower level memory, that we explained that, and also what we explained here, both read and write has cache line replacement situation. So we can make some improvement, okay? Take out the cache line replacement on the write miss, okay, and modify the block will be loaded on next cache read miss. So here is we are modifying the circuit, so eliminate the fact if it is a cache hit, if it is not a cache hit, well, go and write the data directly into the lower memory. We are kind of taking a shortcut here where we bypass the, let's say, L1 cache, and let's say its block is present in L2, we write down there. If it is not even an L2, we bypass that and we write it directly on the RAM. Because we are kind of hoping that that theory of locality won't apply on that address, and will be off for next like many cycles before we need to ever replace the block. Now what if like we need to we need to replace it. Like, let's say that same address now after the write is done, which is not done at the higher level of memories, but it directly done at the lower level of memory. Then if there is a cache miss, then we find the block from the lower level of memory, right, and start copying back. So data consistency problem is no longer there, because it was we made the data inconsistent for the situation where there is a cache miss. Now at the read time, we are copying back from the lower memory, so we are keeping the consistency and delayed it till the next read operation is done. Now cache hit on write still occur, right? Let's say there is a hit on the write operation, then of course there is still the stall, because we write the data in the cache and then still we need to modify the data into the lower level memory. Can we do anything about that one? Yes, we can do something about that stall with addition of write buffers into the memory management unit. So the idea is here, let's say I have like certain addresses that I need to write some data into that address, and we had a miss and that miss incurs a delay because in the write through procedure, in write through strategy, that data has to be written down into lower level memory. So to avoid the stall, if we implement some sort of queuing mechanism, that only control unit, what it does, it basically writes onto this higher level of memory, the top level one, L1 cache for example, and write the same data, or I would say enqueue the same data into the memory management unit's queue, and the corresponding address is also queued, and then it goes back to its own job. So memory management unit, what it does, if it sees that this buffer has some data, or this queue has some data, it will write that data into the memory lower level of the memory. At this point, you possibly can ask, what happens if the queue is full? Then it will go back to the stall. Control unit go back to the stall, and as soon as the queue open up for at least one place, that corresponding data and address will be enqueued again into the memory management unit. So basically, if the queue is full, it basically revert to this original behavior of incurring stall upon write. Okay, in this strategy.